Dear students, welcome to my video class. In this video, we shall continue with this problem. Show that the set R is equal to the elements of the form f such that f from s to z is a function. Okay, the set of all functions from s to z, where s is any non-empty set and z is the set of all integers, is a ring under the operations plus and dot defined by f plus g of x is equal to f of x plus g of x. So like this, f plus g of x is equal to f of x plus g of x. F dot g of x is equal to f of x dot g of x is a ring. Okay. By data, R is the given set. R is the given set consisting of the elements f, where f from s to z is a function. Let us explain this. Suppose S is the given non-empty set and Z is the set of all integers. Okay, so we can define a function f from S to Z such that for any x belongs to x belongs to S, f of x will be in Z. Okay, so here f of x is the image of x under the function f. Okay, and what is f of x? Because this is in Z, f of x is an integer. F of x is an integer. Similarly, you can define function g. Okay, g also maps x to g of x. Similarly, h you can define h maps an element x to h of x. Like this you can define. And you take all these functions f, g, h and so on and consider another set R, okay, which contains the elements like these. All these functions, elements means all these functions are taken here. Therefore, R is defined like this. This is actually the given set R, which contains f, g, h, like that. Okay, all these are functions from S to Z. This is how R is defined. Now let us come back. In R, okay, here two operations are defined, plus and dot. Okay, by the definition in the given problem, how plus is defined? F plus g of x is equal to f of x plus g of x, where f and g are two elements of R, means two functions. Similarly, dot is defined like this. F dot g of x is equal to f of x dot g of x. Okay, so now you take any element x belongs to, no, this is not R, x belongs to S. Okay, for any x belongs to S, f of x is an integer, because obviously for any x is in S, f of x is in Z, f of x is an integer. Okay, now g, if you take g of x will be integer. So then f of x plus g of x, obviously f of x plus g of x is an integer. F of x dot g of x is an integer. Okay, so the sum and product of these two are again integers. So recall, sum and product of functions are also functions. I mean to say, suppose f is a function and g is a function, f plus g is again a function. Similarly, f dot g is again a function. So sum and product of functions are also functions. So from this, what do you conclude? You have two elements f and g in R. F plus g is again in R, f dot g is again in R. Therefore, R is closed under the operation plus. So closure law is true under plus, also under dot. Okay, so closure law we have verified with respect to both the operations plus and dot. This is the first thing we need to do to claim the properties of rings. Now let us come to associative law under the first operation plus. For that you take three elements f, g and h in the given set R, and x is an element of S. Now we have to climb, actually we have to climb f plus of g plus h is equal to f plus g of h. For that we have to consider this. See, f plus of g plus h of x you take. Okay. Then this can be written like this: f of x plus g plus h of x. This is by the definition of plus in R. This is how you take the definition of plus, you can define like this. Okay. Now again using the same definition, see, g plus h of x, g plus h of x is written like this: g of x plus h of x. Now these f of x, g of x and h of x are integers. You remember, these are integers. So you can club like this: f of x plus g of x of h of x. This is because of associative property in Z. Because these are integers, associative property yields this result. Now, excuse me. Now, again using the definition of plus in R, see, this f of x plus g of x can be written as f plus g of x. Okay. And similarly, if you continue, this again you can club f plus g of plus f plus g of plus h of x. You can club like this. Okay. Then this is how the final result comes: f plus of g plus h of x is equal to f plus g of plus h of x. Okay, this is for any x. This is for any x belongs to S. Therefore, you can generalize this as f plus of g plus h is equal to f plus g of plus h. This is true for any f, g, h belongs to R. Therefore, what do you conclude? Associative law holds in R with respect to plus. Now we shall come to identity law. Okay, identity law under addition. Let us define a function. See this one, like fg, you can define another function. So this is your, this function is O of x is equal to 0. What do you mean by this? O of x is equal to 0. O brings every element to 0. That is like this. Okay. Here you take S and Z. Okay. Like we have defined f, g. We are going to define some other function O. Okay. This O is defined such that you take any elements of S. You can take x1, you can take x2, you can take x3 and many elements. All these mapped onto only 0. All these mapped onto 0 under this function O. I mean to say, O brings every element of S to 0 in Z. Okay. So therefore O is an element of R. O means it's a function. Therefore it's an element of R. Now for any f in R and x in Z, consider f plus O. Okay. So f plus O of x is defined like this: f of x plus O of x, that is by the definition of plus, and that is equal to f of x plus 0. This is by the definition of O of x. O of x is equal to 0. And here you note f of x and this 0, they are integers. Okay, obviously f of x plus 0 is equal to f of x, and what do you conclude? F plus 0, sorry, F plus O is equal to F. Similarly, we can claim O plus F is equal to F. This is nothing but, see, F plus O is equal to O plus F, that is equal to F. You recall the definition of identity law, okay? A plus E is equal to E plus A is equal to A, something like this. If you take this F as A and this O as E, you can compare. Therefore, what do you conclude here? Okay, this element acts as the identity element. This means, the function O acts as the identity element in R. So, identity law holds with respect to plus in R. Now, we shall come to inverse law under plus. For to claim inverse law, let us take an element F belongs to R. An element F in R. For any F, you can always expect minus F in R. Okay. And this minus F is defined like this. Minus F of X is equal to minus of F of X. Note the difference here. This minus F of X is equal to minus of F of X. Okay. It is defined like this, such that here F plus minus F, if you club these two, of X. Okay. This is actually F plus minus F is another function. Okay. For two functions F and minus F, F plus minus F is the function, that is another function. So this of X you can define, that is equal to F of X plus of minus F of X. And by the definition of minus F of X, it is like this. F of X is as it is. This minus F of X is written as minus of F of X. And note down here F of X, they are same and they are integers. Because of this minus, that should be 0. Okay. This 0 can be written as O of X by the previous definition. Okay. Now, what we have claimed? F plus of minus F of X is equal to O of X. So, this is true for any X belongs to S, that yields this F plus of minus F is equal to O, where what is O? This is the identity elements. You recall this? A plus E is equal to, A plus B is equal to E, something like this. Okay. So now what do you conclude? Similarly, we can claim this. Minus F plus F is equal to O. So from this, you can write like this. F plus minus F is equal to O. That is equal to minus F plus O. It is similar to this. A plus minus A is equal to E. That is equal to minus A plus A. Here E is the identity element. Therefore, this should be the inverse of this. Something like this. Therefore, minus F should be the inverse of F under addition. Okay. Therefore, minus F is the additive inverse of F. So, what do you conclude? Inverse law holds in R with respect to plus. Now we shall come to commutative law under addition. You take two elements F and G in R. F comma G belongs to R. You consider, actually you are going to prove like this. Okay, you are going to prove F plus G is equal to G plus F. Okay, to claim this you need to prove F plus g of x is equal to g plus f of x. Okay, for all x belongs to S. Actually, you have to claim this. For that, I have considered f plus g of x. That is equal to f of x plus g of x. That is by the definition of plus. And this f of x and g of x are integers. Therefore, we have written f of x plus g of x as g of x plus f of x. Because commutative law holds in z under plus. Again, by the definition of plus, that can be written as f plus g of x. So, what we have claimed? See this f plus g of x is equal to g plus f of x. This is for all x belongs to S. Therefore, f plus g is equal to g plus f. This is nothing but commutative law. Therefore, commutative law holds in R with respect to plus. So, because of these properties, we claim R is an abelian group under addition. So, next. Now, let us come to associative law under dot. So, as we have proved associative law in plus, similarly, we can prove associative law under dot. For that, you have to consider this. Let us explain this. Okay, you have to prove this. F dot of g dot of h, okay, of x is equal to f dot g dot h of x for all x belongs to S. This is what you have to claim. For that, I have taken f dot of g dot h of x. One more bracket should come here. Okay, one more bracket here, like this. So now that is equal to, by the definition of dot, f of x dot of this of x, g dot h of x. Again apply the same definition here. Okay, so this g dot h of x is g of x dot h of x, and look, f of x here, f of x, g of x and h of x, they are integers. Okay, so we can use associative law here, and you can club like this, and again you use your definition dot, so you can club like this. Okay, similarly you can continue like this. Okay, so we have arrived at this point. F dot of g dot of h of x is equal to f dot g of dot h of x. This is for all x belongs to S. So you can conclude like this. This is equal to this. Therefore, associative law holds under dot in R. This proves the associative law. Now, let us come to distributive law. So, we shall prove both left and right distributive laws. Okay. So, you take three elements F, G and H in R, and X belongs to H. Let us consider this. F dot of G plus H of X. Okay. And we have to claim that is equal to F dot G plus f dot h of x, that you know. So now first we shall apply the definition of dot here, dot. Okay, you have used the definition of dot here. Okay, that is f of x plus g plus h of x. Again you can use the definition of plus here. So here this can be written like this, and note f of x, g of x and h of x all are integers. You can apply distributive law here, that is dot distributes over plus. f of x dot g of x plus f of x dot h of x, because these are integers, and in case of integers distributive law holds. Okay, that is the reason, because left distributive law in z. So again you can use the definition of dot here also, and you continue like this. What we have claimed, f dot of g plus h of x is equal to f dot g plus f dot h of x. This is for all x belongs to s. Therefore you can arrive at this result. Okay, you can arrive at this result. Now, therefore we conclude left distributive law holds in R, and you can similarly continue with right distributive law. You don't need to explain like this. You can write similarly. We can claim right distributive law holds in R. This is enough if you write like this. Okay, so because of these two, what do you conclude? Distributive law holds in R. Okay, so we have claimed all three main properties of rings. Okay, now what do you conclude? R plus dot is a ring. Okay, we have proved R plus dot is a ring. That's okay. Now further you have to continue to prove this. You have to verify whether commutative law under dot holds. I mean this R plus dot is commutative or not, commutative ring or not. You have to claim, you have to prove this commutative law with respect to dot. Further, the existence of unity. I mean, is that R plus dot a ring with unity, or is that R plus R a commutative ring? You have to claim these two. Okay, thank you very much.